Okay, thanks everyone for coming. We're happy to have Evan Grohs here for the first seminar of the fall term. Evan's an expert on all things neutrino transport, applied both to astrophysical systems and in particular the early universe. He will tell us about some of that work today, some extensions of that work that he's already done in that area. And before I forget, we will be taking Evan out for dinner tonight, so if you're interested in joining, please we'll probably meet here around 6 or so. And take it away.
Thank you, Joel. Like Joel said, my name is Evan Grohs. I'm a postdoc at University of Michigan. I have an ongoing collaboration here with Joel and with Dick and George Fuller, who's my graduate advisor who was my graduate advisor at San Diego. So very happy about the work that we're making. What I'm going to talk about today is actually some of the work that kind of motivated the project that Dick and Joel and I are on, and also some of the future work that I plan on doing with my code, which is called Burst. So I'll first just talk about what the goals of the Burst code and the Burst project are. I'd like to just give you a rundown of some of the things we've done over the last 3 years or so with Burst. And then I want to talk about in the future what we plan on doing moving from a Boltzmann transport approach into the quantum kinetic equations, which are actually evolving both the energy and the flavor wave functions of the neutrinos. And then I'll conclude at the very end of this talk. So just a couple useful constructs that probably a lot of you in cosmology are familiar with, maybe not with my specific notation, but definitely know the physics behind this. I use something called the co-moving temperature parameter. This is not a strict temperature in the thermodynamic sense. Instead, this is just an energy scale that redshifts with increasing scale factor. A lot of times you'll see this called the neutrino temperature, but we're going to avoid that kind of notation because we're very interested in how the neutrinos go out of equilibrium where there is no temperature. So as the universe expands, the neutrinos redshift in their energy. So we use this quantity epsilon to be the ratio of a neutrino energy to the co-moving temperature parameter, and this provides a co-moving invariant. So we can bin our neutrino distribution functions with this epsilon parameter, and it simplifies the differential equations that evolve those epsilons. So when we talk about the neutrino distribution functions, or the neutrino occupation numbers, this is this quantity f here, which is just related, which just relates the momentum phase space density to the number density. So Burst, the genesis of Burst, was an idea between George Fuller at San Diego, who was interested in neutrino physics, and Mark Paris at Los Alamos National Lab, who is interested in high-precision nucleosynthesis in the early universe. And they wanted to make a code. They wanted to have a project, right, where they could combine both of those in order to do high-precision neutrino cosmology. So the acronym here for Burst, I will be talking a little bit about BBN, about making, predicting primordial nuclear abundances. Unitary, in this sense, means a, what do you call it? It's unitary in the sense of the T matrix. All right, so this is like a conservation of probability. This is not the same as conservation of baryon number. Every nuclear reaction network conserves baryon number. If it doesn't, then it's not physics. All right, so this is a different sense in like trying to use the differential cross sections, all right, within a nuclear reaction network to maintain unitarity between those in order to give high precision predictions on the abundances and on errors, theoretical errors on those abundances. Recombination is just kind of our way to eventually get this code into a more robust way to actually predict CMB kind of observables. Self-consistency is something that we're always trying to maintain by evolving the spectra and trying to predict cosmological observables based on that spectrum. And transport is what I'll be focusing on in this talk. And this is actually following, the evolution of neutrino spectra by energy. And later, I'll talk about actually doing it by flavor. So this is more of an advertisement than anything else. Don't worry about the numbers, okay, on this plot. They're just supposed to show these different kind of quantities versus a decreasing co-moving temperature parameter or equivalent to an increasing time. And these 4 different quantities I'm looking at are kind of indicative of 4 different epochs in the early universe, right? So this is the entropy per baryon in the plasma. It's indicative of something called weak decoupling, where the neutrinos go out of equilibrium as compared to the electrons and positrons. Y sub e is the electron fraction, and this shows how the neutron to proton ratio is changing and how the neutrinos, once they go out of equilibrium with the plasma particles, still maintaining an equilibrium with the baryons until later times. Positron-electron annihilation, for the most part, is when a positron and electron annihilates into 2 photons. Also, positrons and electrons can annihilate into a neutrino and an antineutrino, which is important in the weak decoupling epoch, right? So this is just looking at this ratio, co-moving temperature to plasma temperature. Basically, the plasma temperature heats up as the co-moving temperature multiplied by the scale factor would just be a co-moving invariant. And then finally, this is just the deuterium, the relative deuterium abundance with respect to single proton hydrogen. And I have this epoch called the nuclear freeze-out epoch. Most of the time, you'll hear this called the Big Bang nucleosynthesis epoch. I'm trying to get away from that kind of nomenclature. Like, in my opinion, that if you want to be able to do this epoch, if you want to be able to predict the abundances to high precision, you have to do all of this, right? So all of this, in my opinion, is BBN. And I didn't really care about the numbers so much as just like the qualitative features of these curves. As you can see, these curves don't completely, aren't completely coincident, but they absolutely, have an overlap here. And so this is what we're getting at with self-consistency, evolving the neutrinos throughout these 4 different phenomena, okay? So just as the final plug, Grant Matthews calls this Astrophysics 101. And it's really it's indicative of so much that astrophysics can do, how rich this is. So this epoch, this phenomenon here, weak decoupling, is the weak interaction between neutrinos and charged leptons. Weak freeze-out is a weak interaction between the leptons and the baryons. Positron-electron annihilation is basically an electromagnetic interaction between the charged leptons and the photons. And nuclear freeze-out is strong and electromagnetic interactions between the baryons. So you have all 3 you have 3 of the fundamental forces there, and then all of these start off at equilibrium and eventually freeze out once gravity, your 4th force, overwhelms these rates. So you have all the fundamental forces in this picture. So to start with some of the work that we've already done, let me briefly talk about weak decoupling, how the neutrinos go out of equilibrium with the positrons and the electrons. So I have 2 different sides to this slide. All right, the left side is the instantaneous approximation, and the right side is actually using Boltzmann neutrino transport. So in the instantaneous case, at a high temperature, right, you would set the co-moving temperature equal to the plasma temperature. I have 10 MeV here, but it doesn't necessarily need to be exactly 10 MeV. The neutrinos preserve their Fermi-Dirac shapes. So in this case, this co-moving temperature parameter does kind of act like a neutrino temperature that I have here in the Fermi-Dirac expression. Using conservation of entropy, one can show that at freeze-out, the final ratio of these 2 energy scales is 4/11 to the 1/3. And you'll see this number ubiquitous throughout this talk and throughout any sort of neutrino cosmology presentation. So this is how the neutrinos would instantaneously decouple from the plasma. Now, to do this properly, you actually follow the out of equilibrium energy transport. And so what I have here, right, is actually the reactions that the neutrinos are experiencing with the plasma particles. For those of you that are interested in neutrino physics, you might ask, well, why don't you have neutrinos scattering on nucleons? Those are much larger cross sections, much larger energies given the nucleon rest mass. But the entropy of the universe is very high, so there's very few baryons around. And so that's not the main driver on what keeps the neutrinos in equilibrium, right? It's actually the charged leptons. And so using just standard electroweak field theory, you can calculate amplitudes for all of these processes and then write down a derivative for the occupation number as a function of those amplitudes, the fifth power of the co-moving temperature, and F, which is just the statistical factor. It's basically just the occupation probabilities and the Pauli blocking factors, the 1 minus Fs, if you're familiar with the Boltzmann theory. So you'll notice here that I specifically wrote 2 integrals. This is a 9-dimensional integral, but due to the symmetry of the early universe, the homogeneity and isotropy, you can reduce this down to 2 dimensions, which will be important later on when we discuss quantum kinetics. So taking these numbers, right, and then integrating these derivatives over their phase space, multiplying by energy, you can calculate what the change in the energy density is. And so this is weak decoupling here, right? The fact that this is not identically equal to 0, right? That there is a flow from the plasma into the neutrino seas. And this energy flow, right, you can write this equivalently as a change in the entropy per baryon of the plasma. So this is a decrease in entropy of the plasma. This is the result. This slide is the result of a neutrino transport calculation. And so in this case, what we have on the horizontal axis is our epsilon parameter, and on the vertical axis, this is just kind of the relative change in the differential energy spectrum. So this is basically just telling you how much these curves differentiate or deviate, I should say, from equilibrium. So here we have a scenario with no oscillations. So we have an electron neutrino bump in the spectrum and a muon neutrino. The tau is completely degenerate with the mu, and then the antineutrinos are completely degenerate with the neutrinos in this scenario. There's no asymmetry within the neutrino sector. If you integrate these curves, right, you'll find that the changes in the electron spectra are a little less than 1%, and in the mu spectrum, a little less than 0.5%. TCM over T, all right, is this value right here. For comparison, 4/11 to the 1/3 is 0.7137. So this is showing, in a sense, that the neutrinos are slightly warmer than what you would expect in the standard cosmology. I'm sorry, in the no transport, in the instantaneous treatment of weak decoupling. So what we were able to do 2 years ago is we did the calculation of neutrino transport. That had been done before, but we did this self-consistently while calculating the abundances, which hadn't been done before. Most people had always post-processed nucleosynthesis using the out-of-equilibrium distributions. And when they did that, they found, right, that there was very little change in the helium number. All right, just a few parts in 10 to the 4, which is consistent with what we found. So this was not really a surprise. People expected that in the group. What we didn't expect, though, was the change in deuterium. Now, again, this isn't a very large change, right? Less than 0.5%. But it's an order of magnitude larger than helium, which was surprising. And this was actually missed in the 10 years before we tried this calculation. People had done it, but they had missed actually the change in deuterium. And this is important because deuterium is one of the pillars. The accurate prediction of deuterium is one of the pillars of the standard cosmology. So this Schramm plot over here has the baryon density, which you could relate to the entropy per baryon on the horizontal axis, and then different relative abundances and the helium mass fraction. So these curves, right, just show how these are theoretical predictions of how these abundances and mass fractions change with baryon number. This orange line here is the baryon density as given by Planck first data release, which is on this plot, it would be the same as the more recent data release. And then these hashed regions that you see in these different parts of the plot are the observed abundances given by astronomers. So deuterium here, right, you can see how tight this error bar is and how our prediction is almost right on top of this, right, for the baryon density as given by Planck. And what you're seeing here, this change in deuterium, is actually due not so much to the change in the neutron to proton ratio from the out of equilibrium neutrinos. It's done because of the entropy, how the entropy changes in the plasma. Deuterium, as you can see, is very sensitive, all right, to the entropy, right? Written down here as baryon density, but equivalent. You can see the sensitivity here. And so that's actually what's causing most of the change in deuterium. So this plot here just shows the decreasing co-moving temperature parameter versus these different entropies in these 3 different sectors, right? So as the neutrinos decouple, heat flows from the plasma into the neutrino seas. So the decrease in the plasma entropy is accompanied by an increase in the neutrino plasma. Overall, adding these two together, the total entropy of the universe increases, as it must, according to thermodynamics. Now you can see the kind of precision I had to use in order to generate this plot. So it's not a very big increase, but nevertheless, it certainly does exist. So we've already talked about how the neutrinos decouple from the electrons and positrons, but again, the baryon component is at a much lower density given the high entropy. And so neutrinos do not decouple from the baryons in the same way that they decouple from the charged leptons. So this process of decoupling from the baryons is weak freeze-out. Again, 2 halves to this slide, an equilibrium treatment and then a Boltzmann treatment. So the neutron to proton reactions are given as these weak isospin flipping reactions with neutrinos, antineutrinos, electron flavor, and then electrons and positrons. So you have the 4 lepton capturing reactions, and then you have free neutron decay plus the 3-body reaction to produce neutrons. So if you make the approximation that these rates are very fast, you can write down this equation for chemical equilibrium. This relates the chemical potentials of these 4 different species to one another. And so from this, just using standard statistical mechanics, you can calculate what the ratio of the number density of neutrons to the number density of protons. This is called the N to P ratio, and it's a function of these degeneracy parameters, right? So this is just the chemical potential of nu E, right, divided by temperature, and this is the chemical potential of mu E divided by temperature. And then also related to the difference between the neutron and proton rest mass. In the standard cosmology, these are both nearly 0, and so this is the term that dominates. And so you can see as the temperature drops, right, the neutron to proton ratio also decreases until you get to the scenario where the neutrons are incorporated into the helium nuclei. I also have here written just the electron fraction, which is just the number of protons divided by the baryon density, which you can relate to the neutron to proton ratio like that. So we see, right, that the temperature is decreasing, and so the neutron to proton ratio is also decreasing. To do this properly, right, instead of just using this equilibrium expression right here, you actually have to calculate these rate coefficients for these 6 different processes. So unlike weak decoupling, where we had a double integral, the rate coefficients for weak freeze-out are actually only a single integral. And this is just due to the fact that you're making an approximation that the baryons are very non-relativistic and have basically infinite rest mass compared to the energies of the neutrinos and the charged leptons. So again, you have your co-moving temperature to the 5th kind of dependence, and this is just schematic here. You could have F nu E, but you could also have 1 minus F nu E, right? So this is the F nu E part, and then this is blocked, 1 minus F nu E. And so just to reiterate, this is important to calculate this neutron to proton ratio correctly because most of the neutrons will be incorporated into helium. And so the mass fraction of helium is related approximately to the neutron to proton ratio as given here. So this plot is supposed to show the dependence of the 6 different neutron to proton rates on a decreasing co-moving temperature parameter. So these solid lines here are the neutron destruction rates. And then the dashed lines are the neutron creation rates, equivalent to proton destruction. You'll see here this dotted line. That's just the Hubble rate for comparison. So what we see here, right, is that at high temperatures, these rates are very fast, in both directions, compared to the Hubble rate. So we would expect equilibrium up here. Once you get down to about an MeV or so, you see how these rates fall below the Hubble rate. So you naively just expect that once they fall below the Hubble rate, you wouldn't expect that the neutron to proton ratio would change much until you get it maybe to later times when the free neutron decay rate, all right, can influence the neutron to proton ratio. You may notice here that this red solid curve is not perfectly horizontal. This is actually due to the fact that you have Pauli blocking, the 1 minus Fs, are actually significant at high temperature. If you don't include that, I don't have a plot on this, but if you don't include this blocking here, if you just assume that this is a constant rate with temperature, you actually find a 1% difference in helium. So this is important. This little deficit right here is important to 1%, even though it's much lower than the Hubble rate at those high times. So what I want to give you guys is, let's just consider, for pedantic reasons, all right, or pedagogic reasons I should say, this altered scenario of weak freeze-out. We'll calculate the weak rates until we get down to a user-specified weak freeze-out temperature. At this temperature, we'll just stop calculating these rates. Okay? Now, this obviously is never how you would code something up like this. This is just a sensitivity study. We want to see how sensitive the neutron to proton ratio through the helium mass fraction is to these rates. So at the weak freeze-out temperature, we'll set all these lepton capture rates, all 4 of them. We'll just set them to 0 and see what we have. And as you can see here, all right, that if we go down to, you know, a couple hundred keV, 700 keV or so, and set those rates to 0, our prediction would be off by 35%. Now, I know that doesn't seem like a lot, but in CMB, S4, we're aiming for 1% kind of precision on some of these abundances. So it's showing here, right, that albeit you'd never do this calculation, all right, it shows just how well you have to do the calculation on the neutron to proton rates in order to get accurate helium. So the neutron to proton rates for weak freeze out are sensitive to the occupation fractions of the neutrinos and the antineutrinos. So many people have posited that the universe has an asymmetry in the lepton sector, which is given by something called a lepton number. So the lepton number for a species, for a flavor I, right, is just the number of neutrinos minus the number of antineutrinos for that species, normalized by the number of photons. In general, when people have done these calculations in the past, they do this at a high enough temperature such that they can see oscillations in the neutrino spectra. And they don't carry this down to low temperatures where you would actually start getting effects on the abundances. So what we did here, right, is we tried to introduce a new quantity called the co-moving lepton number, where basically instead of using the photon number density here, we use some sort of canned neutrino number density. Basically, all we wanted here is that these energy scales, or these particles, their typical energy scale is the co-moving temperature parameter, whereas this is the photon temperature. And so we didn't want that 4/11 to the 1/3 kind of hanging around. And so we just used this co-moving lepton number, which as you can see is dimensionless. In the case, right, where you don't have any oscillations, you only have the Boltzmann transport, you can't change this number. Okay? Any sort of reaction that we were looking at earlier with weak decoupling preserves lepton number in the incoherent limit. And so this quantity here should be a co-moving invariant. As you go through weak decoupling and electron-positron annihilation, whereas this quantity does not. That's why we're using this quantity. I should have said that this isn't just purely for intellectual reasons. There are physical motivations for positing this existence of this asymmetry. Basically, if there are sterile neutrinos of masses 1 electron volt or so, you could have a matter-enhanced MSW resonance around the weak decoupling epoch. People in the past, specifically Jim Neller and Gary Steigman, have put limits on the lepton number and have actually suggested that helium may prefer a lepton number that's different than 0. And finally, actually just creating the baryon number in the first place. Certain theories predict that you have to have a lepton number in order to do that. So for leptogenesis and baryogenesis, this is also a motivation for having a non-zero lepton number. So, absolutely.
Focus on this remarkable statement you just made about the sterile neutrino, that 1 electron volt is going to actually have a big impact on this.
If that state even exists. I mean, there's controversy on whether or not.
Well, no, I'm just interested in 1 eV having such a big impact at those high temperatures. And that's just because it's the delta M squared is such that the oscillations are relevant to the time scale over which
Well, so again, if there was that state, that 1 electron volt, and there was no lepton number, then you wouldn't worry about it. It wouldn't be there. What's important is the lepton number, because that gives you, all right, an asymmetry in your density term of your Hamiltonian operator. I'll talk about this later, right? So it isn't necessarily the mass, Dick. It's a combination of the mass and the lepton number itself, all right? If you change those around, okay, this MSW resonance could be at GeV, TeV, or equivalently, it could be at EV. So does that make sense? Like, it's important not only what the mass is, but what the asymmetry is.
But you're effectively injecting an asymmetry in terms of decay.
For what I'm doing, absolutely. I'm just saying there was an asymmetry. How that was created, right? That's the work of particle physicists. All right. If there was needed for something like leptogenesis or baryogenesis. I was just, when I made this comment, it was more just looking at like what would a MSW resonance do for the abundances, is what I was more interested in. Thanks for pointing that out, though. So this plot, this is from a paper that George, Mark, and Chad Kishimoto and I wrote that did the transport, the Boltzmann energy transport for non-zero lepton numbers, and looked at what the changes were to the abundances. And so it's prohibitive from a computational cost to do a parameter scan in the co-moving lepton number. And so what this plot shows is a couple of squares and dots, which actually are the full transport calculation. And then we made a model. We mocked up a model of a little bit of extra dark radiation to try and simulate the change in N effective for these different non-zero co-moving lepton numbers. And as you can kind of, I think you can see fairly well, our model worked really well to predict what the abundances were at these decade values of the co-moving lepton number. So these, with a higher lepton number positive, that means you have more neutrinos, which means you increase the neutron destruction rates and decrease the neutron to proton ratio. And you can see that all 4 of these abundances or mass fractions that we're looking at are sensitive in the direction of decreasing the neutron to proton ratio decreases the abundance, and then vice versa for a negative lepton asymmetry. This figure of merit that I've been using, about 1% changes in helium-4 deuterium. This is just the sensitivity. I'm not predicting that this is what the lepton number needs to be to match abundances. I'm just saying that if you saw a 1% difference in deuterium, let's say, all right, that would be consistent with a lepton asymmetry on the order of 10 to the minus 2. All nuclides are more sensitive to the negative asymmetry, except for lithium-7. Kind of see that here, just how the red and the magenta lines cross there, whereas they don't cross there. This is tantalizing for people who are interested in the lithium problem, the fact that lithium is overproduced. But in order to decrease lithium by about 75%, you would need to go to a lepton number that would be close to unity. And deuterium and helium ruled that out. So this is not a new statement, but for those of you who are interested, lepton numbers by themselves will not solve the lithium problem. So to get a little bit more into this thing I've already mentioned called, this parameter called N effective, want to talk to you about about some of the things that go into it. So N effective is given by this definition of the radiation energy density as a function of the plasma temperature. Theoretically, you could calculate what these things are at any sort of epoch, but for the most part, you use this after positrons and electrons have annihilated, so that you only have the ionization electrons. You don't have the relic Cs of the charged leptons. The way it's defined, you would naively think, right, that N effective would be 3 for 3 flavors of neutrinos. They would be non-degenerate. Lepton number would be 0. And then finally, the temperature of the neutrinos would be 4/11 to the 1/3 of the photon temperature. So to give just a simple little calculation that we did, if you're trying to calculate the ratio, this co-moving temperature to plasma temperature, and going for higher order effects than just entropy conservation, you can show that this ratio is 4/11 to the 1/3, and then the correction from it. And this correction here is due to the fact that when you conserve entropy, right, the electrons do not have a zero rest mass. They do have a non-zero mass. And so if they decouple at a certain temperature, right, this is what the correction is to the energy scale ratio. In addition, there's plasma effects from a different equation of state than radiation. And so this quantity right here characterizes these finite temperature quantum electrodynamic effects, where alpha here is just the fine structure constant. Now, as you can just kind of estimate, right, that this is not going to be a very large number. But if we solve this equation up here for N effective, right, the relative change in this ratio from 4/11 to the 1/3, right, does go like the 4th power. So it will change it, you know, at a larger scale than what's just in here for the ratio. In addition, I have, you know, just another term here for if you have a Boltzmann transport and the neutrinos go out of equilibrium, then you have this delta rho for just the extra energy density induced from the heat flow from the plasma into the neutrino seas. So we were interested in how this ratio changes, and unfortunately, we don't have really the sophistication to model these finite temperature QED effects to any more precision than what's already given in the literature. So we just made up a mock calculation where we wanted just to see how sensitive this ratio is to the mass. And so we changed the value of the rest mass. We're not advocating here for any sort of time variation of the fundamental constants. Again, this is more of just a sensitivity study. And this is really just to see kind of the pattern here, right, and the scaling. These finite temperature QED effects you can think of as dressing the electron rest mass in medium, and we wouldn't expect, you know, changes on, you know, from the actual value up to an MeV. It would be smaller than this, but it still gets the point across. So these curves here, right, just show the ratio of co-moving temperature parameter to plasma temperature as a function of the decreasing co-moving temperature parameter. And we start off here at unity, and we end slightly larger than 4/11 to the 1/3. where an increase in electron mass actually increases the ratio of this temperature value. So N effective, there's two effects here, the change in the ratio and also the change in the energy density. N effective increases, right, as you go from low electron mass to high electron mass. You might think that actually you could get the opposite, because the higher the electron mass is, that means the lower density of electron-positron pairs that you have. But lower density, right, is because they're more massive, and when they annihilate, right, they produce more energetic neutrinos and antineutrinos. So overall, that's the dominant effect here, and that's why N effective is increasing. All right. Thank you all for your patience thus far. This is what I've done the last couple of years. Are there any questions thus far before I move into quantum kinetics? Okay. So as I think most people are aware, the flavor eigenstates and the mass eigenstates of neutrinos are not coincident. And so because of this, you have non-zero mass differences between these eigenstates, and you end up with neutrino oscillations. So to describe this, everything I've done thus far has basically just assumed neutrinos are massless and have no difference in mass. All three of them are just massless. What I'm going to do now is assume that like the neutrinos still kinematically, you can ignore the rest mass, but for the oscillation part, for actually the coherent evolution, you need the mass differences. And so the way you represent this is using a generalized density matrix. And so the generalized density matrix has dimension 2 number of flavors by 2 number of flavors. The 2 is just from the 2 helicity states. Neutrinos are left-handed, antineutrinos are right-handed. There still is the right-handed neutrino state and equivalently the left-handed antineutrino state. I'm just calling those opposite helicity. I'll also call them inactive states. You will sometimes hear those called sterile neutrinos, but that is different. The sterile states of the active neutrinos are different than the sterile neutrinos that are thought to exist at 1 electron volt or maybe 1 kilo electron volt or so. So this density matrix, right, is 6 by 6. These here are block 3 by 3 matrices, right? The diagonals of FLL are the occupation numbers that we have talked about in detail up until this point. The off diagonals of FLL are the flavor coherence terms that you're familiar with from oscillations. And then FLR, this has to be a Hermitian matrix. So FLR here is what's called spin coherence. So it's basically the coherence, right, between the 2 different helicities of neutrinos, right, and then for F bar, the 2 different helicities for antineutrinos. So if we do not know right now what the character of neutrinos are, if they're Dirac versus Arana. The definition of Dirac here is that neutrinos and antineutrinos are separate particles. In that case, if you were doing a full-blown quantum kinetic equation, you have to evolve both F and F bar, right? Like I said, this is a Hermitian matrix. So you have 42 equations of motion here, and then if you bin it in energy, in angle, you can see how many equations you're going to have, right? This very quickly becomes a supercomputing kind of problem. If, on the other hand, neutrinos are Majorana, then that means that they are actually their own antiparticles. So you don't need F bar. You can just pick the phase of the right-handed antineutrinos such that you can use this script F matrix right here, where you have neutrinos and you have antineutrinos. Given the form of the quantum kinetic equations, it's typical to write this as a transpose. It's just a notation thing. Phi here are those spin coherence terms. These will not be populated in any sort of isotropic environment. You have to have an anisotropy in order to populate this. And in 2015, Srigliano, Fuller, and Vlasenko actually showed a really neat result for Majorana neutrinos and how you could populate this off-diagonal, this off-block diagonal matrix. So by definition, the quantum kinetic equations are the evolution of this 2NF by 2NF generalized density matrix. So this is obviously supposed to just be symbolic, how you write this equation. There's actually, like I said, there's dozens of equations actually within this. This is just the matrix form of it. Over here, right, let me just give you kind of a general overview of what's supposed to be represented here. This D is just your Vlasov operator showing how the phase space evolves for the occupations, for the density matrix rather. I here is just the square root of -1. H is called a Hamiltonian-like operator. This gives the coherent evolution. So H in this case, right, can change the neutrino flavor and it can change the helicity. So this is a unitary operation. You can't change the number of neutrinos. Unlike the collision operator, right? So the collision operator, this is the incoherent part, and this will change all the properties of the neutrino density matrix, right? The flavor, helicity, the momentum, and the number. So this is manifestly non-unitary. So these equations are beasts to solve. If you're interested in the core collapse problem, they're looking at literally millions of coupled ordinary differential equations, coupled partial differential equations. In the early universe, however, okay, regardless of whether these neutrinos are Arana or Dirac, you have no anisotropies. So the coherent, the spin coherence term is identically equal to 0 in this kind of environment. And so what we were doing in burst, right, we were evolving these occupation number arrays, you know, one each for electron, mu, and tau. And now we're taking those into these two matrices, right, where you actually have off-diagonal flavor coherent elements. Again, in the early universe, no spatial inhomogeneities, right, no direction anisotropies. The Vlasov operator simplifies immensely. All right, if we use our definition of epsilon, all we have here is a full time derivative of f as a function of epsilon. And so here, H, again, Hamiltonian-like operator, and just a change in notation, C hat are the collision terms. So I'm not an expert on the literature on this. I think from looking at it, this Hamiltonian term has been known for probably at least 20 years, if not maybe 30 years. Sigel and Rafelt are some of the first people to really work on this. On the other hand, the collision term, even in the early universe for the simplified form, this hasn't been known until 2016, when Blaschke and Srigliano calculated what this is. And so this is a seminal work in the field of neutrino quantum kinetics. So to give a little bit of instruction on what goes into the coherent term, there are three individual terms. You have vacuum for vacuum oscillations here, right? M squared is your mass, your Arana mass squared matrix, and U is your PM&S matrix, which encodes the mixing between the mass and the flavor eigenstates. H sub D is your density term. This term here is proportional to the lepton asymmetries that we talked before. L tilde in this case is actually the neutrino lepton asymmetry, and L is the charged lepton and nucleon asymmetry. And so in the early universe, you would expect these both, you would expect this to be 0 and this to be fairly close to 0. And then finally, this term is oftentimes ignored, but it's important if you're going to actually do this with collisions. This is the thermal term, and it's given actually not by the asymmetry, but by just the total energy density, again, for the charged leptons and for the neutrinos. So you can see that this term here, Dick, what you were asking before goes like the first power of G Fermi. This is a one loop correction, whereas this thermal term here, I know it's kind of weird the way I have it written, but this is the 2 powers of G Fermi, one from here and then 1 over the W mass squared is on order G Fermi. So this is the coherent term. For the incoherent term, it's a little bit more complicated. So we already talked about how to do this in the Boltzmann transport case. The beauty of what Blaschke and Srigliano did, right, is that they were able to show that the matrix elements, which they don't write as a matrix element, but it's this equivalent expression right here, is actually the same for the Boltzmann transport as it is for the quantum kinetic expression. What they did is they invented this clever technology, right, on how you go from what I had before, which are just vectors, so to speak, right, into matrices, right? So this curly bracket here, right, is actually the anti-commutator. You can see here. And what you have here also is a trace function. So this encodes, the fact that neutrinos of the same flavor have a higher amplitude of scattering than neutrinos of differing flavors. So this right here is just for this example, neutrino scattering on other neutrinos. There's also neutrino scattering on antineutrinos, and then neutrino scattering on electrons and positrons. And so you can write down all these collision terms. I have this written down here as a 9-dimensional integral, but like I said, you can reduce this to 2 dimensions. And this was actually kind of the benefit, is that I didn't have to do anything different, right? Since my matrix element was the same structure, I didn't have to do anything different when I actually went to reducing these integrals. All I really had to do was replace what I had with vectors with this matrix technology. And so because of this, we're working towards this quantum kinetic code. Now, I gave up immediately on the supernova problem, right? Like too many arrays, all right, to do it with energy and with angle. And I gave up on the early universe problem too, at least initially, right? And so let's just consider a slab. No geometrical boundary conditions, only neutrinos and antineutrinos. So this is not the early universe, right, where you have a time dependence in the metric, right? This is just not, this isn't physical, okay? But it gives us a way to test these expressions for the collision term in the quantum kinetics. So I'm going to show you guys some plots and movies looking at this normalized differential number density. So basically, this is just.
Go back to the equation. I'm just trying to follow through where the matrix aspect of C is here, since it's really dn ij, where it's running over all of the indices, including the. And so the trace, there's so many brackets there.
I know it's hard to, it was really hard to tech up, okay? Just imagine how difficult it was to code, all right, Dick? So there's an implicit identity matrix.
Okay, good, right.
Okay, so you just put this along the diagonals, right? Then add it to these actual matrices. This one here is an identity matrix. This is all 3 by 3, or n flavor by n flavor. None of this is 6 by 6.
So everything's really simple with that trace, it just pulls up. So, yeah, okay. All right, I get it. Okay.
I'm happy to talk to you about this and show you what Blaschke and Srigliano did. Their paper is not easy to read, but.
Depend here on the, or is it?
No, it doesn't. No.
Why?
It's, I can't answer that question. I don't know why that is. But this, before, when people had done mock-up quantum kinetic equations, okay, they just guessed on what the off-diagonal elements are of this collision operator.
Well, that's not the issue. I mean, I can figure all that stuff out. It's just that the thing that's surprising is that M doesn't depend upon the various states that are coming in. And
this is only good right up to second order in G Fermi. I don't know what it is for higher orders. I mean, G Fermi that's a small number. So that's why we're only going to second order here. Okay, if you're just interested in the coherent evolution and you jack these numbers up, right? Well, okay, jack this number up by introducing an asymmetry. You wouldn't even need to look at it, right? This would be the dominant effect.
Anything that, mean, we're used to matter enhanced.
Yeah, this is matter enhanced.
Neutrino oscillations. But I'm just wondering if within those other terms there's any effective damping of that activity.
That was always the assumption. Okay, people just said that the off-diagonal terms, okay, in this matrix are just damping coefficients, right? So they, instead of calculating any sort of integral here, they just multiplied it by a number, right? So you have some sort of complex number, okay, on the off-diagonals of this matrix. You multiply that by a number, right, that which is negative, and it just damps the amplitude of that. That's what people had always assumed.
So they have done this calculation, and so
This is purely theoretical. Blaschke and Schrigliano, right? There's no actual computations, no computer computation. They just wrote down the equations.
They did the formalism, but they didn't actually calculate the rates.
I'm not trying to brag here, but that's because there wasn't a code to do this, and I have a code now that can do it. It's yeah, with the quantum kinetics, right? So it calculates the entire evolution of that density matrix. There's no approximations, okay?
Does that mean that you can get an effective damping rate?
Yes. Well, we can see how well it actually does damp, how well that approximation works. And that's actually work that George's graduate students are working on, okay, is looking at that approximation, all right, which is, that approximation has been used for the last 15 years. Okay, I'm trying to go one step further, all right, get rid of the approximation and then comparing to their results. So, like I said, this is ongoing work, and so we'll do the slab, we'll do the early universe, and then the graduate students in the audience can do the supernova problem. So I want to show you a movie, but just let me try and set up the background for this, right? So at time t equals 0, we have this infinite slab, so it's homogeneous and isotropic everywhere. We're looking at this normalized number density. Okay, we'll start with the electron neutrinos in a Gaussian. All right, and the muon and the tau neutrinos in Fermi-Dirac equilibrium at a temperature of 8.6 MeV. This is normalized. This Gaussian is normalized such that it's the same number of electron neutrinos as mu and tau. We won't allow oscillations, so we'll just test the Boltzmann transport. So this should be consistent with what I've done in the past with my codes, right? Because with Boltzmann transport, right, all you're doing is evolving the FII. You're just evolving the diagonal elements, okay, of this matrix. And so if this matrix is diagonal, this one is also diagonal. There is no coherent term, right? That's just 0, and all you have is collision. And again, in this picture, right, the mu and the tau will start off degenerate, and the neutrinos and the antineutrinos are completely degenerate throughout the entire calculation. Okay, sorry, that's not a very good. I think you guys can get the idea. Not a very good aspect ratio, but as we let time go forward, okay, you see a decrease here in electron neutrinos and an increase in the temperature of the mu and the tau. So we don't have any sort of oscillation. So the only thing that is interacting here are neutrino scattering off of other neutrinos, which that interaction is not flavor blind, but it's identical for mu as it is for tau if they start off in the same distribution. So there isn't any difference here between mu and tau. You'll notice, right, that the peak is coming down here, right? The peak isn't as large as it was, but there's more probability out here in the tail. So overall, the number density and the energy density are conserved. The number density is a few parts in 10 to the 5. The energy density is a little better, a few parts in 10 to the 10. So this is the case with no oscillations. So that's just Boltzmann neutrino transport. Okay, so now if we go to the case with oscillations, you can see the breaking of the degeneracy, right, between the tau neutrinos and the mu neutrinos. So you can actually see that green curve. And what you end up seeing eventually, right, is there's more, this looks slower just because there's more frames per wall clock second. But what you're seeing here is that the equilibrium is maintained again, and it's exactly identical to the equilibrium in the Boltzmann case. But I don't know if you guys paid attention. For the Boltzmann case, it's about a millisecond. And for this case, it's about half a millisecond. And so it's actually faster with neutrinos. And the way I think about this very simplistically, from like a statistical mechanics perspective, is that you have more channels on how neutrinos can change flavor, right, when you put in oscillations. They can't change energy, all right, but they can change flavor, and so that's why this is actually going at a faster rate. So I'll be candid with all of you and just boast. This is the first time anybody has ever done a truly self-consistent quantum kinetic calculation. Now again, there's a lot of qualifiers on that, right? Because I'm doing this in a slab, all right? I'm not allowing there to exist electrons and positrons, right? It's still very canned kind of calculation, but it's completely consistent with using neutrino density matrices as compared to using the diagonal elements and damping the off-diagonal elements, which is what's been done before. Okay. That's fine. So, to conclude, I hope at least you guys maybe are a little bit intrigued by what burst can do and what it will be able to do in the future. So again, I'm not the only one on this project. I kind of do the lion's share of the coding, but a lot of the theoretical work is done at Los Alamos with Daniel, Vincenzo, and Shashank Shalgar, who's a postdoc at Los Alamos. In addition, George is the main lead here at UCSD, and he has graduate student Luke, and Chad Kishimoto is a professor at University of San Diego. And also we work here. Alexi's more of a theorist. He's a postdoc at North Carolina State. We'd like to make this code available for a public release in the future. That date's still to be determined. There's still a lot of work we need to do in the nuclear reaction part of the code, making a unitary network. And I hope that you saw that like these slab calculations are pretty interesting. That's obviously not the early universe, but we're working to put this into burst, such that we can evolve the neutrino density matrices during weak decoupling. And so part of that, right, will just be to do the transport. And eventually, the quantum kinetic equations aren't only the transport rates, they're also those weak interaction rates with baryon, the neutron to proton rates. There are QKEs for that, which there's still a lot of theoretical work that needs to be done on that. So with that, thank you all for your attention. I'm happy to answer any questions that you may have.
All right, thanks very much, Evan. Any questions? Karen?
So you mentioned supernova, even though you didn't talk much about it. Do you have a sense now with the work that you guys have been doing for the last several years, how important including oscillations and these quantum kinetic effects are going to be in the end?
So I don't know the answer to that question, and anybody who does know the answer is lying, right? I hear a huge range that like it's not really that important, okay, to it being the dominant effect on like how a core collapse actually explodes. You see what I'm saying? Like it runs the gamut. I don't know how good the calculations are, like from the Oak Ridge group and the Munich group, those are the two leaders in the field. And they certainly have a sophisticated calculation. But, I mean, first of all, they don't have a lot of these equations in their code because these Vlasenko, Fuller, and Trigliano is 2014, and Blaschke and Trigliano is 2016, right? I mean, we just haven't known what these equations are for a few years.
Even a few years before that, when people were first beginning to talk about incorporating neutrino oscillations into the simple neutrino transport that they were doing in those calculations.
So again, right, if they're doing that, if they're trying to evolve a density matrix, okay, they're using a lot of approximations, okay? They don't have any sort of that spin coherence that I was talking about earlier with like a Arana neutrino, flipping from neutrino to antineutrino. That's new from 2016, right? That's less than a year old. They wouldn't have that kind of calculation. They wouldn't have the collision term for the off-diagonal, right? They would have some sort of just damping coefficients that they're used. It's probably a good approximation, to tell you the truth. That's what I'm kind of seeing thus far on what I've been doing, but I worry about that.
Is there any barrier to checking the prediction of 3.046 once you get charged leptons?
So no. I should, just to be a little bit, I'm sorry, I don't know why this is looking like this, that this, where was it? That this canonical prediction by Mangano from 2005 includes neutrino oscillations using some sort of damping coefficients on the off-diagonal terms. They claim that doing this with just Boltzmann transport, the way I've done it in the past and the way I'm getting now, does not change anything to, you know, some decimal way down in here, right? That's their claim. I'm suspicious about that. But have to do, that'll be, you know, definitely a section of the first paper, right, that we write on early universe QKEs. Just to follow up on that, I actually think the differences in these numbers really aren't from neutrinos. I don't know if Mangano is correct and like he's saying, oh, it doesn't make a difference. It makes some difference, but I actually think that those finite temperature quantum electrodynamic effects, which aren't very well understood, or at least aren't very well worked out, will actually make a bigger difference on that number. That's my opinion.
I think one important thing is to know what is the uncertainty, right? Like how accurately are we predicting these things? And that's something Mangano doesn't do. They don't say within what range do we make this range.
Good point.
Okay. Yeah.
Going back to the simulation you showed with the thermalization in a slab. So how does, so you said that when you have neutrino oscillations, then the thermalization is faster. So how does it scale with the energy gap between the two species?
I'm sorry, what do you mean by energy gap?
So you, for example, if you put one species of neutrino, one energy, and another species of different energy.
Oh, you're asking if I move this Gaussian to
To the right or to the left?
So, that's an interesting question. I really haven't thought about that. The more energy difference there is, if you move this to the right, the faster the rates are, but the neutrinos also have a longer ways to go to get into that equilibrium distribution. I mean, so, you know, the final state was something that looked like this. If you move this further over to the right, okay, the final state is going to look like that, right? So, I mean, the Gaussian would actually dictate what the chemical potential would have to be. So, I don't know. I can just tell you this is pretty easy. If you scale this energy, right, you just make this larger, the rates are faster, right? These rates go like 5 powers of temperature. So doubling this rate, right, is a factor of 30 increase.
And the effect of neutrino oscillations be as important as it is this energy if you just scale up the energy?
No. So the oscillations, right? In order to see oscillatory behavior, you have to have a non-zero off diagonal, okay? And that's where this U matrix comes in. So that's important there to like start populating that off diagonal. But higher energy, right, means higher momentum, which means that overall the amplitude of this potential gets smaller. So I already did the calculation for 100 MeV, and in that case, it didn't matter. Oscillations didn't do anything, okay? Similarly, I did a calculation at 10 keV, and oscillations were the dominant thing, right? That was going to take forever to run because the collisions scale like 5 powers, the oscillation scales like an inverse power of temperature. So you kind of had to find a sweet spot in order to make an aesthetically pleasing movie.
So I'm glad we went back to this slide because I didn't understand, these have to be operators so that we can do the commutator.
Mm-hmm.
And it's not clear to me, HT doesn't really look like an operator.
These are matrices, right? So this matrix here is the sum.
Well, I guess I don't need the details, you just answered it. So it's a funny matrix representing energy.
Yeah.
Oh, okay.
Right. Those are matrices, so this is a matrix.
So it has the same indices.
Yes. This is what I was trying to say to answer this gentleman's question, is that these are just diagonal matrices to start with. Okay? And so that commutator is it just vanishes. Right? In order to get the off diagonal elements populated, you have to have this vacuum term. This vacuum term, right, is sensitive to the differences. I have it here written as the absolute square of the mass, but you can just subtract off an identity matrix. And that's why that's why we care about delta M12 squared and delta M13 squared. I'm sure you know this, Dick, but.
Well, you're also convincing me by the details that I thought that one could split the problem. We discussed this before, and essentially after each incoherent term, that you could transport it in SI states for a while and then go back to the collision and all that stuff.
So
it looks like it's too mixed.
I will certainly agree in the limit, right, that you want to do a accurate calculation. Okay? Now, what people have done in the past, right, they said, you know, as especially the case with a non-zero lepton number, right, they say that this is a bigger term. This is G Fermi, right? And this is G Fermi squared. So what they'll do, right, is they'll say like this rate is not as large as this other rate. And so this rate right here. And so what they'll do, all right, is they'll take a time step, they'll calculate that nasty collision term, and then they'll take 100 more time steps where they only calculate the coherent term, and they use the same value. They say like the rate isn't changing that much over the next 100 time steps. And people claim that they get the same results as doing the full-blown calculation. That's the claim.
That's what people
But
would do if they were trying to do a Monte Carlo study.
But that's tuned, Dick. That's tuned, right? Because they're using these damping coefficients, and they pick those damping coefficients specifically so that they can do that. So I wouldn't. They might be right. I'm not saying that they're wrong, okay? But it bears testing their approximations.
All right, maybe that's a good place to stop. So as I said, we'll take out another minute tonight. So